Hi viewers, here we'll start with the next part of this series in which for this video we are going to deal with the next type of motion, that is curvilinear motion. And when we are going to think of curvilinear motion, we particularly will be thinking of kinematics of curvilinear motion. In the previous video, we have seen what is rectilinear motion and how to analyze the particles in rectilinear motion considering the kinematics. Now, here we'll deal with the next part of motion, that is kinematics of curvilinear motion. What is curvilinear motion exactly? As we said before, that if it is rectilinear motion, it has to be the motion along straight path. In the similar manner, if we will define curvilinear motion in simple words, we can define it as the particle when it travels along a curved path is said to be in curvilinear motion, or in other words, a particle following a curved path is defined to be in curvilinear motion. Now, when we think of analyzing such motion, that is motion along the curved path, we have to analyze it considering the three systems of coordinates. The first system is the rectangular system of coordinates, or it is also called as the Cartesian coordinate system, in which we are going to think of the x and y planes. The second system is the normal and tangential system of components, which is also called as the path coordinate system, that is n and t are the directions, normal direction and the tangential direction. And the third system is the radial and transverse coordinate system, or it is also called as the polar coordinate system, that is r is the radial direction and theta is the transverse direction. So these are the three systems: first Cartesian system, second path coordinate system, and third polar coordinate system, in which we will be thinking of analyzing this particular motion, that is curvilinear motion. Now, what are exactly the rectangular and Cartesian coordinates? If we think of here, the diagram is shown x plane, y plane, or x axis, y axis. This is the xy plane, and in this xy plane, if we consider a particle to be at a point z whose coordinates are x and y and whose position vector is denoted as r bar, in that case that position vector will be written as r bar is equal to xi plus yj, I and j are the unit vectors along x and y axes. As per rectilinear motion, we know the velocity is nothing but the differentiation with respect to time or change in position with respect to time. Then v bar will be, from this definition we can write v bar as dr bar by dt, and after differentiating it we get it as v bar is equal to dx by dt I plus dy by dt j, wherein vx, that is the component of velocity along x-axis, will be dx by dt, and the component along y for the velocity will be dy by dt. Therefore, we can write the velocity vector as v bar is equal to vxi plus vyj. Similarly, as per the definition of rectilinear motion, we know a bar is equal to d square r bar upon dt square, or it can also be written as dv bar by dt, and therefore we can write it as d by dt of this v bar, that is vxi plus vyj. Is it? And further, to find the components of acceleration and acceleration along x and y direction, we will further differentiate it and then get the components of acceleration along x and y direction as ax is equal to d square x by dt square and ay is equal to d square y by dt square, which again ax can be written as dvvx by dt and ay will be written as dvy by dt. Therefore, we have the components of acceleration along x and y direction, that is, it can be further written as a bar is equal to axi plus ayj. Is it? So in this way we can find the rectangular components of velocity and acceleration. This was for the Cartesian system of coordinates. Now if we further think of the second system, that is the normal and tangential system, or you can say if we try to express it in the form of path variables, then in that case the velocity components, we have to note that the velocity components in curvilinear motion, the velocity always acts tangential to the path. In curvilinear motion, the velocity always acts tangential to the path at any instant, at any time, and therefore the component of velocity along the tangential direction is always equal to the magnitude of velocity, and the component of velocity along the normal direction is always 0. Again I repeat, as in curvilinear motion, the velocity always acts tangential to the path at any instant of time. Therefore, the tangential component of velocity is always equal to the magnitude of velocity, and the normal component of velocity is always equal to 0. Now, if we move on to finding the tangential and normal components of acceleration, as we said, at will be written as the tangential component of acceleration and an will be written as the normal component of acceleration. Therefore, at will be equal to differentiation of velocity dv by dt, and an will be equal to the velocity square by the radius of curvature, magnitude of the velocity square by the radius of curvature at that particular instant. Dear friends, how to find the radius of curvature? There are two formulas by virtue of which we can find the radius of curvature, and those are: first, rho is equal to mod of rho. It is radius of curvature is always positive, therefore we have to take its mod, and it will be calculated as 1 plus dy by dx square whole raised to 3 by 2. I again repeat, in bracket 1 plus dy by dx square whole raised to 3 by 2 totally divided by d square x by dx square, or it can also be calculated as vx square plus vy square whole raised to 3 by 2 divided by vx ay minus ax vy. Again I repeat, Vx square plus Vy square whole raised to 3 by 2 divided by Vx Ay minus Ax Vy. Now I have to think about the directions of these two, the sense of, the nature of the directions of these two. So here I have drawn a curve. There are two curves, I can say. One is with a positive curvature, other is with a negative curvature, or I can say it can be represented as a vertical sine curve. Okay. Now friends, in this case, one important thing that I have to remember, I have to tell you, is that about this particular point wherein the curve changes its sign or changes its direction, or the particle changes its direction of curvature. That point, at that instant, at that particular instant wherein the particle seems to change its direction of curvature, is called as point of inflection, is called as point of inflection, and there the radius of curvature is always equal to infinity, and there radius of curvature is always equal to infinity. Therefore normal component of acceleration over this point at the point of inflection is always equal to 0. Again I repeat, the normal component of acceleration at the point of inflection is always equal to 0, since the radius of curvature is infinity and the direction or the particle changes its direction of the path or sign of its path. Okay. Now the second thing, the tangential component of acceleration is considered to be positive when it is acting along the direction of motion. When it is acting along the direction of motion. If it has to act in the direction opposite to the motion, then AT will be considered negative. The second thing that you have to remember, AN, that is the normal component of acceleration, is always positive and has to be directed towards the center of the curvature. Has to be directed towards the center of the curvature. Normal component of acceleration is always directed towards the center of curvature. So this has to be remembered. This particular point where the radius of curvature is infinity, at that point AN is 0 and radius of curvature is infinity, is called as point of inflection. So up to now we have seen two systems. Now we will move on to the third system, that is the polar coordinate system or radial and transverse components. So here V bar, the velocity vector, is written as r dot e bar r plus r theta dot e bar e theta, where e bar r and e bar theta are the unit vectors along the radial and transverse direction. Therefore, the velocity along radial direction is r bar and the velocity along transverse direction is r theta bar. In the similar way, if we go for the acceleration along the normal direction, it will be r double dot minus r theta dot square, and if we go for the acceleration along the transverse direction, it will be 2 r dot theta dot plus r theta double dot. So these are the components of acceleration along radial and transverse direction. So here these were the three systems in which we can find or analyze the transverse, or you can say the radial or the normal or the tangential or the Cartesian systems of coordinates for curvilinear motion. Now we will see a simple problem related to this. The first numerical that we have to focus on is the velocity of a particle is defined by Vx is equal to 100 minus t raised to 3 by 2 and Vy is equal to 100 plus 10t minus 2t square. Determine the radius of curvature first at the top of its path and second at t is equal to 12 seconds. So here this is the question. Again I repeat, the velocity of a particle is defined by Vx is equal to 100 minus t to the power 3 by 2 and Vy is equal to 100 plus 10t minus 2t square. They have asked us to find or determine the radius of curvature, that is rho, at the top of its path and at t equal to 2 seconds. There are two questions. So to solve it, first we will list out the given things. What are the given things? Solution will say Vx is defined 100 minus t2 to the power 3 by 2 and Vy as 100 plus 10t minus 2t square. The questions are rho at the top of the motion and topmost position and rho at 12 seconds. So the first case, when we say it is that we have to find the velocity or the radius of curvature at the topmost position, we should know conceptually that the vertical component of velocity is always 0 at the topmost position. Therefore, equating, this is the conceptual part, to find the radius of curvature at the topmost position means we should know at the topmost position the vertical component of velocity is always 0. Therefore, we will equate Vy to 0 and get at what time does this component reduces to 0. So that is, we substitute. So from this, after equating Vy to 0, we get t equal to 2.5. What we have done, we have equated Vy to 0 and we obtained t equal to 2.5. So after substituting t equal to 2.5, we will find that Vx is equal to 96.04 meter and Vy is equal to 112.5 meters per second. Therefore, we know the formula Vx square plus Vy square whole raised to 3 by 2 and Vx Ay minus Ax Vy. So we have obtained Vx and Vy. Now we have to find Ay and Ax. So to find Ay and Ax, what will we do? We will differentiate this. And after differentiating, we will substitute t equal to 2.5 in the equation for Ay and Ax. So here, after differentiating, we get Ax as minus 3 by 2 raised to 1 half and Ay 10 minus 40, and in this two equations, if we substitute t equal to 2.5, we get Ax as minus 2.37 and Ay as 0. Therefore, the value of rho that is obtained is equal to, by substituting it in the formula that is the values for Vx, Vy, Vx ay, ax, vy at t equal to 2.5, we get rho is equal to 12095 meters. In the similar case, we have obtained the equations for Vx. These two equations are given. Ax and Ay we have derived. So in all these equations for Vx, Ax, Vy, Ay, we will just substitute t equal to 12 and get the value for Vx, Vy, Ax, Ay. Substitute them in the formula for rho and we will get rho bar or rho is equal to 308.24 meters. So in this way we can obtain the values for the radius of curvature from the given equation. So here we will move on to the next problem, friends. Dear viewers, the next problem which had appeared for 4 marks in the SPPO exams of May 2014, it states that, or it is having a question as a particle moves in a circular path of radius 0.4 meters. Calculate magnitude of acceleration A of the particle if its speed is 0.6 meters per second, but it is increasing at the rate of 1.2 meters per second in each second. This is important part. But it is increasing at the rate of 1.2 meters per second in each second. So here what they have given is, they have given you the value of tangential component of velocity, that is at. The rate increases at 1.2 meters per second in each second. Second means second square, and therefore it is 1.2 meters per second square. So here solution given is rho is equal to 0.4 meters, magnitude of velocity is 0.6 meters per second, and at is 1.2 meters per second square. We know the formula for an. An is v square by rho. V is given 0.6, therefore 0.6 square by rho. Rho is also given 0.4, therefore, and at is given. So if we substitute the value of at and an, we will get A is equal to 1.5 meters per second square. How simple it is it? So if we see over here, that is an we are getting as 0.6 square by 0.4, which is equal to 0.9 meters per second square. At is given, it is 1.2. Therefore, by taking the square of 1.2 square plus 0.9 square, we get the value of A. That is, the question it was magnitude of acceleration. It is 1.5 meters per second square. So this is the required answer to the question which seems to appear for 4 marks.